Okay, so which camera? There is a camera. No, this is the camera is this one. That's it. Hello, hello. Okay, okay. I would like to. It's 4 o'clock already. We are a bit late, but thank you all for joining in through the YouTube Platinum Jubilee channel, the TIFR Platinum Jubilee channel in YouTube, as well as the Zoom through the Zoom. Those who have joined in, I'd like to welcome all of you for this very special edition of the NSF Wednesday Colloquium. So this particular edition, we are honoring Professor Dennis Sullivan's work, who this year won the Abel Prize in Mathematics, which is considered the the highest award beyond the Fields Medal in terms of the recognition. I would also like to mention that we are lucky to have contributors from our own community in TIFR, from the School of Mathematics. We have 3 distinguished experts who are going to present the work in 3 parts. Okay, each talk will be 20 minutes, and we will take questions, pressing questions after each talk, and we will take a cumulative amount of questions after all the 3 talks finish. So it's really a treat for us. For those who are not in the field, it's a big treat because we hardly get to hear mathematics talks in the Natural Sciences Faculty Forum. Now, before I go on and just introduce the speakers, I'd like to say that for those who are attending the NSF Colloquium for the first time, the NSF Colloquium actually was a vision pioneered by Professor Homi Bhabha, our founding director of the institute, who thought that it would be nice if all the natural sciences faculty could meet once a week and have discussions, general discussions on topics of relevance and interest within the community, not only in India but internationally. In fact, one of the experts would come in and deliver a talk. And this kind of brought together students and faculty from different branches of natural sciences and allowed for them to talk across the departments. So this was a very, very successful endeavor. We have trained students through this. So this is a very nice way of actually making your vision broad. So now, without further ado, I would like to have Professor Anish Ghosh, who will.
As you know, there's no Nobel Prize in mathematics. So the reason seems to be, the most plausible reason seems to be that Nobel wasn't interested in doing maths, so he left it out. But when Nobel decided to, start his prizes, he made this clear that there's not going to be a mathematics prize. And at that time, Sweden and Norway were one country. So they were sort of 75 years before this. This is the turn of the century before the last. Sweden had invaded Norway and they'd formed some sort of a country together. And when this was announced by Nobel, a famous Norwegian mathematician called Sophus Lie, Lie spelled with I-E, so he was very influential. The Lie group Lie, yes, not the Bruce Lee Lee. This is a Lie group Lie. Okay, so he was a very influential man in Norway, and he persuaded the then king of Sweden and Norway to endow a prize called the Abel Prize, named after Abel, who was a distinguished Norwegian mathematician who died very early of tuberculosis. Then two things happened. First, unfortunately, Lee died. And second, Norway separated from Sweden. So now they had a new king, and this king was less interested in starting the Abel Prize than was the previous one. So then one had to wait 100 years for this to start again. But this time they somehow managed successfully, and it is essentially a lifetime achievement award. Okay, so it's meant for a lifetime of work. And today we will discuss the work of Dennis Sullivan. So the first order of business is to show you what he looks like. It is not a, okay, so this is a headline from a Quanta magazine article about him. And it says, Dennis Sullivan, uniter of topology and chaos, wins the Abel Prize. So this headline is very, I find it very nice because it's eye-catching and more or less accurate. Okay, so this person really did unite topology and chaos. So today we are going to start backwards. We're going to start with the chaos. I'm going to start with the chaos. Sabyasachi will merge the chaos in the geometry, and Mahan will bring up the topology. So this is somehow the plan for the day. And one thing I'd like to say about Sullivan, which of course might be said later as well, is I find it particularly inspiring that all the work that he's got prizes for and so on and so forth, most of it was very unfashionable when he did it. So when he did some of the work that we're going to discuss, these areas were dead. Nobody was interested, nothing was going on. And yet he came in and did some beautiful work and actually restarted them somehow. Okay, so my subject is chaos, and I have another 15 odd minutes. So let me proceed without further ado. So all of us in the sciences, natural sciences, mathematics, we're all interested in chaotic systems. And so when one talks about chaos, one must be careful. What does it mean to be a chaotic system? So today we are going to proceed by example. So no definition of a chaotic system will be given. Whatever we discuss, that will be a chaotic system. Okay, so what we are going to do is think of a space not too big, like a stadium or this room. And we'll, in typical mathematical fashion, keep on adding attributes to the space so that we can do some mathematics with it. So it's going to be a nice space, where nice will mean some nice property. Think of a playground where we are going to play some game. Okay. In this playground, I would like to measure size. So for instance, if I'm playing billiards, I would like to measure the size of the hole relative to the ball. If I'm playing football, I would like to measure the size of the goal relative to the ball, and so on. So this notion of volume, I'm going to call mu, and sometimes refer to it as a measure. Okay, so this term measure is going to recur throughout the three talks. So think of it as a sensible, mathematically sensible way of measuring the size of objects. So if you want to measure the size of an interval, you take the length. If you want to measure the size of a chair, you try to calculate its area, or a box, you calculate its volume, things like this, but taken as mathematicians are wont to do, to its logical extreme. Okay? So that is my measure mu. And finally, the most interesting ingredient is I need some interesting dynamics on this space. Okay? And what I'm going to do is illustrate one result of Sullivan, where this beautiful dynamics creates some interesting mathematics. And this is going to be done by playing a game. Okay, so this paper of Sullivan's is very famous, and it's essentially mathematical game. So I want to describe this game to you. I told you to visualize a football stadium. So when I think of one, this is what comes up. I know it doesn't look like one, but that's why, you know, we're all locked up on the third floor and not allowed to mix with the general public. So this is an example of the mathematical game I'm going to play, but this is not what we'll go to immediately. We'll do a little bit of warm up, okay? And the warm up is the following. So suppose I have a system, maybe this room and the gas molecules in this room. And I tell myself I must investigate and build a systematic theory of chaos for this system. So if it so happens that my system doesn't do anything, namely that is unable to move points from one place to the other, then this would not be a good example of a chaotic system, right? So chaotic system must be able to, in a meaningful way, move things around. And so Poincare, who is a famous mathematician and physicist, already realized this more than 100 years ago, and he proved a result called Poincare recurrence. And it says the following. It says that for any meaningful definition of chaos, you must satisfy the following property. Namely, if you have a part of your space which is not too small, and you let your dynamics evolve over time and let it continue indefinitely, then the orbit of almost every point, where almost every means close your eyes and pick a point, with probability 1, your orbit should hit this not very small target infinitely often. Okay, so it's sorry? Yes. So imagine that we are in this room and we really are very much invested in the oxygen molecules here being spread out evenly. That's very important, right? So one way of measuring this is due to Poincare, who said that if I take a part of this room, which is not very small, so that not very small is what it means to have positive measure. It just means it's not very small. And then I pick a point and look at its orbit under this dynamics. I might be unlucky. This particular point that I picked might be a fixed point or might not go very far. It might get trapped in something. But with very high probability, probability 1, whenever I pick such a point, not only should I hit this once, if I let the dynamics go indefinitely, I should keep coming back to it infinitely often. In particular, if I take a small neighborhood of the point where I started and it's not too small, I should come back to it infinitely often as well. Okay? Yes, yes. The n is the time, the t is the map. So it's a discrete time here. Okay, so this is kind of, it's good. It's a good notion, but we would like a little more complication over here. So it would be much more interesting to have a situation. For example, think of the game Kabaddi, right? So you have a lot of players on a field. The field is a nice size field. And one player is trying to hit several targets, and the targets are moving. Okay, so Poincare's recurrence theorem is a lovely theorem, but it's a stable theorem. The target is fixed. The guy standing there, you go touch him and come back, you won. It's much more interesting if he runs around the field. So what we're going to do is allow targets in this space which are allowed to move around. Okay, and then try to measure the complexity of the system by insisting that my system is able to touch the moving targets, not just a stationary target. So in a mathematical sense, I'm going to ask, is it possible, first of all, is it possible to have a situation where I have a lot of targets and I'm able to hit them infinitely often? And if so, how high is the probability that I'll be able to do this? In Poincare's case, if the target is fixed, It's a probability 1 situation, right? Close your eyes, you're overwhelmingly very likely to pick a point which will hit that thing infinitely often. Now, if I allow that thing to move around, what is the chance that this is going to work out? Okay, so let's warm up with a simple example. And the simple example is I just take a circle. The unit circle in the plane, okay? And on this circle, my system is just going to be rotation by an angle theta. So I take a point, say x0, rotate it by theta, and keep doing this, right? So this is as easy as life is going to get, right? You just rotate something by theta and try to study what happens. It's a small space, it's controllable. My system is clearly well defined, and to you know, avoid situations which are degenerate, I kind of impose a mild condition on the angle to make it irrational. So, you know, if you have a rotation with a rational angle, it will keep, it has a discrete orbit, it will keep coming back to itself. There's nothing much going on there. So I'll take an irrational angle. Irrational multiple of pi, that's right, yes. And now what I'm going to do is, I'm going to take the first step above from Poincare. So I'm going to have a sequence of targets around a fixed point. Okay, so I start with some other point, say y. And around this sequence, if I draw an interval around this point, by Poincare, I'll hit it infinitely often. This happens. Now I'm going to take this interval and slowly shrink it. Okay, and then see whether I can keep hitting it while it's getting shrunk. Okay, so this is the first step of a moving target. The center of the target is fixed, but the target is kind of slowly shrinking towards it. And this is surprisingly not that easy to study. It's kind of sensitive. So, for example, if you allow it to shrink at, say, the rate, say 1 over n log n, then it turns out that with probability 1, you'll still be able to hit these guys. So this is kind of getting smaller and smaller and smaller and smaller. You're rotating continuously, and the game is to keep hitting this, and you will be able to do it. Okay, so this is a fact. Sorry? So I have a kind of a, so the situation, I'm rotating by theta, 2 theta, 3 theta, 4 theta, n theta, and then I'm reducing. However, if I raise this very, very slightly, then it turns out that with probability 1, I will never be able to do it. Okay, so it's a little bit tweak to the system, changes from being a full probability event to a 0 probability event. Okay, so this is an example of chaotic dynamics, and this is what after Sullivan has been called the shrinking target property. Okay, so this is an example of chaos in a system where we try to characterize the chaos by trying to understand quantitative recurrence to targets. Okay, so this is the kind of attempt, and Sullivan, it's safe to say, was one of the pioneers of this. Okay, so how much time do I have?
Actually, 5 more minutes.
5 more minutes? I'll make it. Okay, now I need to do something more complicated to explain what Sullivan did. So I'll just hand wave through it, but it's whatever I'm saying is morally true, if not factually. Factually, it might not be true. So the circle, this circle that we built, you know, how you make it is you take the real line and you wrap it around the unit interval. You take the 0 and 1, join them, and then keep on wrapping. Okay. So this wrapping process, which is called taking a quotient, can actually be done with more complicated objects. And so a more complicated version of the circle is obtained by taking the real line and replacing it with a matrix group. 2 by 2 matrices determinant 1, and taking the integers and replacing them with 2 by 2 matrices determinant 1 and integer entries. Okay. This is a more complicated version of the circle. It's called the modular surface, and it's a kind of a fundamental object in a large part of mathematics. The important thing for us is that it's not like the circle in that it doesn't kind of close up like this. So it's not a compact surface, but it's the next big thing, next best thing. It's kind of not very big. It has a finite volume. So it allows you to do calculus on it without sweating too much. Okay. And this surface comes with a geometry, which is a geometry of negative curvature. Okay, so this is the important thing. Like we took the circle and got the circle by wrapping around the line, you could take to make the torus, you would wrap around the square. Now this wrapping around is happening in a space where the triangles all point inward. Okay, so this is a space, it's kind of a circle, but it has a distinction, it has negative curvature. So here is Sullivan's theorem. It's kind of difficult to state, so I won't state it. I'll show you a picture and explain what happens. Okay, so this is the picture. So here is this modular surface. As you can see, it's not like the circle because it doesn't close up, but it has 2 ends or 1 end or 3 ends, but the ends kind of taper off so that it's not too big. Okay, so what Sullivan proved was that suppose your target was the point at infinity, very far, and suppose that you're playing a game. So here's your surface. You're playing a game where there's a point at infinity and some neighborhoods which are rapidly rushing towards it. So they're shrinking to infinity. And your job is to flow along and catch these neighborhoods. Then this has the same kind of flavor as the circle. So with probability 1, you can do it sometimes, and the rest of the times, with probability 1, you can't do it. And the dividing line is very simple. It has to do with why I carefully manufactured this log n. Those of you who noticed it, one of those series converges and the other diverges. Okay, so the one with the 0.001 extra added on, that series converges. So this means that it intuitively makes sense. For the series of volumes to converge means that the balls are shrinking so fast that you're unable to catch it. But if they're shrinking slowly enough that the sum of the volume diverges, then with a high chance you're successful and you can catch them. There is another kind of angle to this story which I won't have time to explain, but if you ask me later on, I'll tell you. It has to do with how well you can approximate a number like pi using rational numbers. So it turns out that these two problems, getting a good approximation to pi better than 22/7, and this problem are one and the same problem. Okay, all right, so I'll stop here. No, the volumes, you can compute the volumes. If they diverge, if you add up and they diverge, then with probability 1, you will hit them infinitely often. If they converge, then it's too fast for the system, so you miss it.
Okay.
A quick comment.
Yeah.
Yeah, so I guess the Poincare recurrence thing is where it's a constant sequence where the constant is greater than 0, so it's always going to be infinite, and hence a very basic case of this is going to be Poincare recurrence.
Yes,
Is that right, Anish?
that's right. That's right.
Okay, thank you, Mahan. That's a question.
Very nice talk. So I just, from a lay person's point of view. So the chaotic system is then defined as sometimes you will hit it with the probability 1 and sometimes you will not, or either or.
No, so that's a good question. So here I'm moving along shortest distance path called a geodesic. And so the point of view is that in a certain sense, this is chaotic. It's what people call ergodic. So that is true. But what Sullivan introduced over here is a new kind of way of studying this kind of behavior. So as I said in the beginning, I don't attribute the word chaos to a specific property. I view it as some kind of a continuum of properties. And then these kinds of theorems tell us how far along the scale of chaotic we're going somehow. Thanks.
Okay. Well, I think we will move on towards. No. Okay, that's not a problem. Yeah. So we will move on to our second speaker, Professor Sabyasachi Mukherjee. Sabyasachi will continue on, and I think we'll load the. Yeah. Yes. Sure, please.
Okay, yeah. All right, yeah, thanks. Is it working? Okay, yeah, thanks. Thank you for inviting us to speak. So I'll not say anything about Dennis Sullivan in general, although, I mean, one could. So I was fortunate enough to spend a few years in Stony Brook where Sullivan was there. It's very, other than being a great mathematician, he's also a very colorful and interesting person. And one can learn a bunch of things from him. Anyway, but I don't think I'll have the time to talk about all these things. So let me talk about a certain theorem of Sullivan, which in fact made its way to this Quanta article that Anish showed in the beginning of his talk. The Quanta article that covered the work of Dennis Sullivan did talk about this particular theorem. And it is, again, an instance of one of those theorems proved in an area that was dormant for a very long period of time. And then there was a big open question, which is open for many decades. And Sullivan came, and with his brilliant insight, he managed to solve the problem, and then not just solve it. The techniques that he used turned out to be really important in many other situations. So, okay, so let me, in the interest of time, directly go to the setup that we are talking about. The setup is not very different from what Anish was talking about. Okay, I think I have to one click. Okay, fine. Yeah, all right. So I am also going to talk about dynamical systems, like the example that Anish gave. You have a space and you are playing some sort of a game on it. So you have a point, the point is moving under some action, something is happening and the point is moving. And well, those who are familiar with differential equations have seen these kind of things a lot. You have the trajectory of a point. Maybe you want to understand something, flow of a point under some force or whatever. And when you are interested in a discrete time dynamical system, instead of looking at the continuous flow of a particle in time, you want to say take a snapshot of the system every 1 minute. So time 1, time 2, time 3, and you're assuming that the law that dictates how you go from time 1 to time 2 is the same as the law that takes you from time 2 to time 3 and so on. So you have a system and you're playing a same game again and again and again, and you want to understand what's going to happen in future. What's going to happen if I keep playing this game for a long time? Similar to this geodesic flow example that Anish showed. So let's see if I get this right. Yes. So for me, the definitions are not important, but X is my space and F is the rule that takes your current state to the next state, how you go from now to future. And you want to understand what happens to typical orbits, or let's say, why not all orbits, when you keep iterating it under this particular chain. So you start with a point X, your gas particle, you move it, it goes somewhere else after a second, then it goes somewhere else after a second, and you are just taking snapshots every second or every minute, and you want to understand where is this particle going. General questions that one is interested in answering in this setting are more or less these. So where do these orbits accumulate? Are they going to sort of stay in a small box? Are they going everywhere? Are they going to be attracted to something, etc.? The next question, yeah, so here the word chaos comes. You want to understand which orbits are sensitive. So what do I mean by that? This is probably some qualitative way of talking about chaos. So you say that a point or an orbit is sensitive if the following happens. And this is kind of logical. You have a point X, and suppose you know that this point behaves in a certain manner under long time, under many iterations of the map. What if you start with a nearby point, Y? That Y and X are now very close. Will they remain close forever? If they remain close forever, that's a stable dynamical system. The qualitative behavior of the entire path in future does not really depend on your starting point. On the other hand, if it so happens that 2 points are close now, but after, let's say, 100 minutes, they are far apart, that's indication of chaos. That's indication of some non-uniform behavior going on in the whole space. So you want to understand which orbits are chaotic, which ones are stable, and so on. Okay, now I'll not talk about this. The point is that you have a space, the football space, the football field, and you have a rule that takes you from present to future. And in order to do mathematics, as Anish said, you want to impose several structures on that football field. Like for instance, you might want to measure distances, or you want to measure volume, or maybe sometimes you want to differentiate, and so on and so forth. So depending on what structure you're putting on your football field, you want to talk about different kinds of dynamical systems, but you can completely ignore these. The particular example, or the particular setup of this no wandering domain theorem is the following. So here, it's really a football field. I do have a lister here. So you do really have a football field, except that the football field is not finite. It's the entire world. It's a whole plane. The entire plane is your football field now, and the way initial point is going to the next point is by the action of a polynomial. This is very basic. This is stuff that we see in high schools, right? So you have a plane, and you are something very simple. Let's say you're doing something like this. You start with a point Z, and you send it to Z square plus 1, Z square minus 1. That's your law. You start with the point Z, you apply Z square minus 1, then again a Z square minus 1, and so on and so forth. What's going to happen? What's going to happen to most points? Can you describe which points do what if you keep playing this game? You can easily write a program on a computer to see what happens, for instance. The general question is, well, it doesn't have to be this polynomial. It could be anything else, any degree, and so on. So how do we even try to understand typical behavior of orbits under these kind of dynamical systems, these kind of laws? And if you don't like the word Riemann sphere over there, you can read a plane. And if you forget rational, think of a polynomial over there. And the Riemann sphere can be thought of as a plane. The plane is essentially the Riemann sphere because the world of the Earth is the surface of the Earth is really a Riemann sphere. And locally it looks like a plane, but actually it's a sphere. So the idea of chaos, or the idea of stable dynamics versus chaos, led people to, partition the whole space, the whole phase space where the dynamics is going on into two different regions. Green is the good one, and red is the dangerous one. And these names are of the people that actually studied these sets. Both are French mathematicians in the turn of around 1920s. So what is the Fatou set? The Fatou set is basically the part of the whole football field, or the part of the plane where, if you start with 2 points that are close now, they'll stay close forever. So stable dynamics, nothing to worry about. And the Julia set is the complement. That's where you have to be very careful. So for instance, you know a point and you know what this point is doing. Suppose this point is coming back to itself, exactly to itself under 50, in time 50. Can you say anything about a nearby point? Well, no, that's the point of a Julia set. The nearby point will do something completely, drastically different. So neighbors remain neighbors in the Fatou set, and neighbors go far apart in the Julia set. So this is probably sort of one way of capturing chaos. This is the Julia set. You can think of it as the region where chaos happens for this kind of dynamical systems. Okay, I'll maybe give you a simple example. If you look at the map Z square on the plane, you can ask, is there any simple example where I can maybe see what the Julia set and what the Fatou set is? If you recall very simple math from high school, the point is, if you take the Z square map, it's not hard to see that there is a unit circle in the complex plane, which is preserved by Z square. Any point outside the unit circle, if you keep squaring it, it gets large, it goes all the way to infinity. Anything inside the unit circle, it gets smaller, goes all the way to 0. So inside the unit circle and outside the unit circle, the system behaves very nicely. But on the circle itself, the dynamics is actually chaotic. So in this particular example, one can write down the Julia set and the Fatou set. So one can identify where is the stable dynamics taking place and where exactly is the dynamics chaotic completely. However, in general, this is not true at all. So that example was a little misleadingly simple. In general, stuff like this happens. What do I mean here? This is the picture of the football field under some polynomial. And this is another, but forget this one. Let's look at this one. So what is the Julia set here? The Julia set is this very intricate, complicated black boundary that you're seeing. So the green region is in the Fatou set. Dynamics is very nice there. In fact, all these black bulbs that you're seeing here, these sort of box kind of regions, those are also in the Fatou set. The Julia set is the common boundary of the green and the black. So as you transition from black to blue, black to green in this picture, you hit the Julia set. So it looks complicated. It's very difficult to say what kind of a set it is, let alone understanding what kind of dynamics is happening on it. The first thing that one should come to one's mind is what, when one does math, when you do math in high school, you want algebraic structure. You want what do you work on? And you work on with straight lines, circles, ellipses, stuff like that. This object is far from all of those. There's no sense of length. There's no, you can't do differentiation. This object is what's called a fractal, and fractals turn out or sort of crop up very naturally in the study of chaotic dynamical systems. Okay, so that's the state of affairs here. The Julia set where the dynamics is chaotic is rather complicated, but the Fatou set it looks nicer. The green part here, the inside of the black part, etc. And back in the 1920s, so now I'm coming close to the main statement of the no wandering domain theorem. So what's the hope? The hope is that, well, on the Julia set, the dynamics is chaotic. I don't want to try too much. If it's so chaotic, so ugly, maybe I'll not try to understand what's going on there, at least as a up to a first approximation. But the Fatou set is where the dynamics is stable. So can I understand the dynamics, or can I understand how points behave on the Fatou set completely? That's the hope. Okay. Is there a problem? Oh, I got frozen over there or something. Ah, the camera. Okay. Thanks. Yeah. Okay, thanks. All right, now it turns out two things can happen. Let me go back to the previous picture, the actual thing here. So see, for two components, there are infinitely many black bubbles over here. There's one here, one there. There are so many of them. There are lots of black bubbles. And if you pick a point on any of these black bubbles and you apply the map or the law that's changing the position of the point, you go from one bubble to another bubble to another bubble and so on. And two things can happen. Either you start with a point in a bubble and you keep applying the law, and then it turns out that the bubbles fall in a cycle. So you have like 10 bubbles like that, and you go from one bubble to the next bubble to the next bubble, and the 10th bubble along the way is the original one. So you come back like this. Or you might just keep wandering in space. You go from one bubble to another, to another, to another, and you never hit back. You never come back to the bubble that you started off with. And it turns out, if this is the situation, then you are, then it's more or less hopeless to try to understand how points behave, because you're never coming back. You're always going from, one country to another, to another, to another. Your history has nothing to do with your past. How can you say anything about the point? On the other hand, if you keep coming back to your own bubble, this is your land. You travel and you come back to yourself. You travel, you come back to yourself. If this is the pattern, then there are classical techniques by these mathematicians, Fatou and Julia, that tell you exactly how points behave. And I'll not go through these examples, but there is a complete understanding of what might happen if you have this pattern. Then you understand orbits completely. Is it 5 minutes? Oh no, I'll be done before that. Yeah. Okay. So this is what's called eventual periodicity, where you fall in a loop eventually, or fall in a periodic pattern eventually, or this is the opposite extreme, where you keep going from one island to another and never come back to your original island. And the question that Fatou asked, it was in fact, I don't remember, I think it was his question, not a conjecture. He didn't know one way or the other what to expect, because in 1920s they didn't have computers. So they had no simulation. So he asked whether each of these Fatou components, he didn't call them Fatou components, he called them something like ordinary set, I don't remember. But if you start from one of these islands, is there any chance that this kind of a thing can happen? Or will you always have a loop like this? And so this was asked in the 1960s, and it remained open for 60 years. In the 1980s, so Sullivan was in Paris, and he was talking to two other people who were working on this kind of dynamical systems, and he suddenly realized that there is a body of work in other parts of mathematics that contain techniques that can be transported to solve this problem. So stuff that were known in completely different parts of math in the 1960s and 1970s can be used to solve this particular problem. And he proved that, at least for polynomials or rational maps, life is not so bad. You never have a wandering domain. No matter which island you start with, you always come back to itself, the original island, which gives you, sorry, not yet, which gives you a complete understanding of what stable dynamics might look like for rational maps or for polynomials. And I'll not say anything about the proof except for the fact that the situation of a wandering domain gives rise to too much flexibility. And Sullivan's intuition was that this level of flexibility is too much that a polynomial can afford, because if you have a wandering domain, he cooked up a certain way of deforming the polynomial. So you start with one polynomial and make it something else. And if you had a wandering domain, he can construct a very large space of polynomials of degree 2. But the space of degree 2 polynomials only looks like this, maybe another couple of coefficients. So wandering would give you so much liberty that you can construct an infinite dimensional huge space of polynomials of degree 2, which is obviously not possible. So in order to prove the punchline of this statement, again, not yet, the punchline of this statement is that it's a statement about a single dynamical system. You have a law on a given football field, and you want to understand what stable dynamics looks like. In order to answer that question, you have to look at the space of all degree 2 polynomials in its entirety. You can't answer the question unless you look at all of them. This is a general principle sometimes in math where, in order to look at one particular example, you want to look at the collection of all of them, the whole space of them. So this was Sullivan's insight, and this is what's called the Sullivan's no wandering domain theorem. Once people had this theorem, it sort of opened the floodgates and people started working on dynamics of these kind of maps in greater generality, and yeah, it sort of gave birth to it was sort of made a rebirth of the field possible. Okay, thank you.
Thank you very much. Thank you very much. Take quick questions. Yes, come on.
Yeah.
So when you say coming back to the same island, it means doesn't necessarily mean coming back to the same domain on the same island. You have to
Not necessarily
to some place on the same island.
That's correct. You start here on this island. When you come back to the same island, you're coming back here, not necessarily to that point. That's correct. Yeah.
Any other question from the Zoom audience? Yes. Could you unmute yourself?
Yeah.
Yeah, please.
Yes. Can you see me? This is Professor Dua from London.
Yes.
From London at this time. I would like to ask Professor Mukherjee that what you said seems, I'm a biologist, that what you said seems to be working in the biological system. And by using this sort of a system, it can be applied to the biological systems or application of that one? Because once it goes to Julia system, I think there's a disintegration and movement towards senescence. Is there any application which he visualized or you can visualize in the application of this one in biological sciences?
Okay, so I guess all I can say is that early examples of this kind of dynamical systems were given by something whose formula you may or may not have seen, but when we do math, we are told that this is something biologists care about. And maybe they don't, but we are told this is something that looks.
Please focus it. I can't see. Focus it.
Okay.
Yeah. Mm-hmm. Yes. What does it indicate? It indicates to a biologist.
It goes to, so x going to some constant times x times 1 minus x. So what does it mean? It's a model of population growth. When the initial population x is, so suppose 1 is the max population and 0 is the least population. Okay. And x tells you how much population you have. 1 minus x tells you how far you can still grow. And the product of them. Sure. So the point is, this can be used to give a model of population growth, assuming that, if there is a lot already in the system, you're already close to the ceiling, then the population can't grow much. On the other hand, if you only have like few viruses in the population, then they can't reproduce much. So taking these facts into account, one can model some sort of population growth, bacteria colony, etc., using the iteration of these kind of polynomials. And it is exactly these kind of polynomial iterations that I was talking about, iteration of quadratic polynomials. So this is one of the early motivations of looking at iteration of polynomials.
Okay.
Yeah, whether or not it has been effectively used to answer the kind of questions you have on mind, I do not know, but yeah, it's a starting point.
That's right. I understand that part.
Thank you.
Thank you very much.
Thank you. Thank you very much for the question. Thank you. Okay, so we will move on to our final speaker. Thank you very much. Let's have a big round of applause for Sabyasachi. Thank you. Then we have our last speaker is Professor Mahan Maharaj, who is going to join us from the Zoom. Mahan, could you just say something?
Yeah. Can you hear me? But I need to
I will
share
let
my
you
screen.
share screen. I will let you share screen. Could you share screen?
Yeah.
Oh, you're sitting in a very nice hilly area, is it? No, I'm just kidding. You're in France right now? Mountainous region in Paris. Okay.
Oh. To me, while sitting in London, it looks like London part.
Okay. Mahan, can you hear us? So cold, it's frozen. I never knew that mathematicians understand bad jokes.
Yeah, I'm in Paris.
Okay, so yes, Mahan, could you full screen it?
Yeah.
Control L.
I can full screen it.
Control L.
I can full screen it. No, that's fine.
Oh, so this is Mac. Yeah.
Yeah.
It's not happening. It's fine. Please go ahead. I think it's fine. We can scroll down the slides.
Is it?
No.
Is it okay now?
No, it's not full screen.
Okay. Yeah, this is a problem. Okay.
So share the screen. Share the entire screen of your computer. So when you go to the share option, share screen.
Yeah. Then I'll just a moment. Stop share.
Right. Yeah, now you can do the full screen.
Yeah. Okay. Is this better? Or is it the same?
Full screen? Now do Control L or something. Full screen, that option. नहीं वो तो कुछ कर नहीं सकते ना. Okay, it's done. Thank you.
Okay, great. Terrific. Okay, now let me see my viewing options. And yeah, okay, great. Terrific. So yeah, thanks, Jyotishman. Great pleasure to be here virtually. So I'll take off from where Shobho left off. And Dennis basically, what he did, I mean, Shobho mentioned this thing about how he incorporated tools which were used in an area which at that point of time was quite remote from this notion of complex dynamics that Shobho was talking about. And he put two things on a common platform. So what were these two things? These two things were different kind of dynamical systems, and we'll say a little bit about them. Okay. So what you saw in Shobho's talk is this black blob on the left. What is this supposed to be? I mean, essentially, this boundary of this black blob is this Julia set, which is supposed to be some kind of a deformed copy of the Julia set of z goes to z square. So it looks like a kind of a fractal circle, the boundary of this domain. On the right side, you have a green blob. Looks sort of similar. I mean, you can take the thing on the left and you deform and you get the stuff on the right. I mean, both are fractals and it's got some kind of a wrinkled up stuff where you can't really do calculus on the boundary. So what's really the maths that's going on behind these two dynamical systems? First, both are complex analytic, which means they are dynamical systems defined on the complex plane or the Riemann sphere. And in Schubber's talk, what you had was something like f of z equal to either a polynomial or a polynomial divided by another polynomial. So f of z is equal to p of z divided by q of z. These are called rational functions. So ratio of two polynomials. And what was he doing there? I mean, what was Dennis's work concerned? I mean, he was looking at the iterates of this one single function. So essentially, you have one law given by this f, polynomial or rational function, and you want to look at its time infinity behavior. Now, instead of one law, what if we have finitely many laws? Q, well, there's nothing to study. So you look at the simplest thing which has some reasonable hope of some sophisticated behavior. So you look at P and Q, both of degree 1, linear polynomials. Z goes to AZ plus B divided by CZ plus D. There's a little hitch here because the stuff in the denominator could go to 0 for Z equal to minus D by C. Well, so then you say that stuff goes to infinity and you throw in this extra point at infinity. So you're really doing dynamics on the surface of the Earth. Very good. Now you look at not just one of these guys. One of these guys is rather boring, but you allow finitely many players in the game. So you look at, essentially you think of finitely many laws. So these are players which are sort of somehow space-wise distributed. The first guy gives a kick to a ball, then the second guy picks it up and kicks it, the third guy picks up, then maybe the first guy picks up again, etc., etc. So essentially, you look at these, I mean, because this Fi is a particularly simple, they are linear, there's a natural inverse map. See, a quadratic map does not really have an inverse. So Z goes to Z square, when you take the inverse, you get plus minus square root. So you don't really have a well-defined inverse. The advantage of having linear guys, I mean, these linear divided by linear guys, is that it's each map individually is a bijection. It's a one-to-one map. It takes one point to another point, and that point gets uniquely pulled back to the point that you started off with. So you have finitely many of these guys. They generate for what is called a group. So essentially, it's a collection of symmetries. And so then what you are really doing is you look at this entire collection of symmetries that is generated by these finitely many simple laws rather than one complicated law. And you ask for the same thing, same kind of question. What happens when you iterate this by this collection of group elements infinitely many times? And then interesting dynamics emerges when this group is what is called discrete, which means that there aren't too many group elements that come very close to each other, which means what? You have these A, B, C, D. These are like 2 cross 2 matrices. Well, when you multiply them out together, there is no matrix element which is accumulated upon by other matrix elements. Yeah, so this is this algebraic gadget, this collection of matrices is what is encoding your system. And what you want to do is translate to what's happening visually, what's happening on the dynamical plane, what's happening on the Riemann sphere. How do you get these fractal objects? So basically transferring the information from some algebraic coding to some visually transparent object that you can sort of iterate and plot on the complex plane. So there are analogs of the Julia set and the Fatou set in this setup also. So the analog of the Julia set, the place where chaotic dynamics kicks in, is what's called the limit set. What is it? It's basically you iterate some point and look at the collection of points on which it accumulates. Where are the points on the complex plane or the Riemann sphere where orbits accumulate? It turns out that whatever be your starting point, Z, the collection of accumulation points is going to be the same. So this limit set is independent of the original point that you start off with. You start off from any initial condition, and then you run this finitely many laws, infinitely many times, and you're going to accumulate to a single set that's called the limit set. This is the analog of the Julia set in the previous picture. And on the complement, this is this omega gamma, the complement of this limit set, the behavior, the dynamical system is totally well behaved. 2 points close by remain close by throughout their future. So friends once are friends forever. This is this omega gamma, and this is called the domain of discontinuity. And such a group, such a collection of symmetries, this is called a Kleinian group. It's named after Klein. Well, I can't resist saying this. Klein had nothing to do with this. They were all discovered by Poincare, and Poincare discovered them and named them after Klein. Okay. So Poincare has already occurred in Anish's talk. Fair enough. So now let's look at these two things. So there are these clear parallels between this complex dynamics, which is an iteration of a single complicated polynomial, higher degree, non-linear. So z goes to z square is not linear. Whereas on the Kleinian group side, you have finitely many gadgets, each of which is linear. Yeah. And so in the complex dynamics side, what you're really you're looking at the semi-group. You can't quite take inverses. So you look at forward iterates only. So this is called the semi-group of iterates of F. On the right side, what you're really looking at is, since each element is invertible, you get this algebraic structure of a group, and you can compose elements and their inverses freely. On the complex dynamic side, you have the Julia set. On the Kleinian group side, you have the limit set. On the complex dynamic side, you have the Fatou set. On the Kleinian group side, you have this domain of discontinuity. So I've shown you a couple of pictures. The one on the left side, it's very reminiscent of one of the pictures that Shobo had drawn, had shown you. These jewels are sort of the red, blue, and the green jewels are like the domain of this. I mean, they are the parts of the Fatou set. On the right side, things are sort of more regular. You see a bunch of circles, yeah? So they are nice round circles. And this accumulation point, the place where you have these, where these orbits accumulate, that's the limit set. What you should sort of take away from this particular picture is that the stuff on the left looks like a bit of a wiggle on the stuff on the right. Yeah? So essentially, the two pictures are really the same kind of object. You have a map from one to the other by a little bit of a deformation. Now, this is some kind of experimental evidence, but it's just one picture. So let me show you a few more. And this kind of parallel between the complex dynamics world on the left and the Kleinian groups world on the right, they come up all the time. Here is another another two pairs. The one on the left is a Julia set. The one on the right is a limit set. The one on the top is there is a sort of a clear analogy between these two, and similarly for the stuff at the bottom. Yeah. So these kind of empirical similarities between the way the dynamics looks, between the way the locus of chaotic dynamics, whether you call it the Julia set or the limit set, well, they seem to have a similar kind of shape. Yeah, that was a kind of an empirical observation. Definitely Fatou was one of the people who noticed this and asked whether there are more distinct parallels. And it was, okay, so finally, this is my last picture which shows this similarity. And there's again, it's a different kind of a dynamical system, but there is a dynamical system which comes from iteration of polynomials. And there's a dynamical system which comes from iterating finitely many rational guys, linear polynomials. And so the question was asked whether this is just some whimsical thing, whether it's a serendipity, or whether there is some deeper factual analogy between these two different kinds of dynamical systems. And so what happens? So it turns out, and this is where Dennis really made a very major contribution. I just think of this. I mean, think of just one polynomial z goes to z square, and you have two different guys, z goes to z plus 1 and z goes to 1 by z. Yeah. So you have two guys, both are linear on the right side, and you have just one z goes to z square on the left. Looking at it algebraically, there isn't really much you can say. But the dynamics, once you plot on a sphere, they look very similar. And in the Kleinian group world, it turns out that this group gamma, it acts very nicely on the domain of discontinuity, and it acts as a family of conformal symmetries, which means it preserves angles. It doesn't preserve lengths, but it preserves angles. As a result, what happens? You can quotient out. This is an operation that Anish had spoken about. You quotient out, which means you remove the extra symmetries and you look at one gadget where you have already gone modulo those symmetries. So that's this quotient of this domain of discontinuity omega gamma by this group of symmetries gamma. So that turns out to be what's called a Riemann surface, which means locally there's a notion of angles. Locally there's a conformal structure. And then we have this theorem which preceded Dennis's theorem. This is by Alfors, Fields medalist, one of the first two Fields medalists way back in 1936. He proved that the quotient is actually a finite type Riemann surface, which means it's really the kind of two-dimensional surface on which Anish was doing his dynamics. They are finite volume gadgets, and they don't, I mean, the stuff is not allowed to go off to infinity. So this is what finite type means. Think of it as just something that has finite volume, which means stuff cannot go to infinity. Stuff has to recur, time and again. Yeah, this was essential. I mean, the quotient dynamics on this domain of discontinuity. This was the theorem that Alfors proved, and this really is one of the sources of inspiration for Sullivan's no wandering domains theorem, which Sabya just talked about. So you have on the complex dynamics side Sullivan's no wandering domain theorem, and on the Kleinian group side there's Alfors's finiteness theorem, which preceded Sullivan's theorem. So it's not just that you have empirical similarities between the two different kinds of dynamical systems. There are actual mathematical facts where one is an analogy of the other, and both can be proven as theorems. Fair enough. One point that Sabya had made is that in order to prove Sullivan's no wandering domain theorem, you really have to study the whole family. This brings us to the next feature, and it turns out, and this is something that is really special about the Kleinian group's world, is that what were we looking at? We were looking at these symmetries, Z goes to AZ plus B by CZ plus D, where A, B, C, and D are possibly complex numbers, which means you're looking really at SL2C. If this P bothers you, forget it. It's not very important. It's the 2 cross 2 matrices with complex entries and determinant 1. And that particular matrix group is the group of what are called Mobius transformations. That means these rational polynomials of these rational maps where both the numerator and the denominator are degree 1. But they are the same as the conformal symmetries of the Riemann sphere. That allows us, and this was known for a while, this is known to Poincare, for instance, that actually allows us to go up one more dimension, which means go up to 3 dimensions and come up with this space of negative curvature. Anish's talk dwelt on negative curvature in 2 dimensions mostly. Well, you have to, if you go up from 2 dimensions to one more, you get 3 dimensions, and you get what is called hyperbolic 3 space, which is a way of measuring, which gives you a way of measuring distances. Think of hyperbolic, think of the upper half space, x, y, z, with z greater than 0. With this metric that I've written there, it's just a Euclidean metric, dx square plus dy square plus dz square, but the whole thing is scaled by z square. So as you go towards z equal
Hello. Mahan, we can't.
Zero.
We are losing you.
Actually, really.
Mahan, we lost you.
Hello. Oh boy. Oh
Hello,
boy.
Mahan. He realized. He realized.
Yeah, I can hear you.
Yes, yes, Mahan. We lost like maybe 30 seconds. Could you again share the screen? But audio. Unmute yourself. Unmute yourself. You're mute. Yeah.
Yeah.
Could you
Now it's
reshare your
okay?
screen? Reshare your screen.
Yeah, I'll do that.
Sorry.
Just a moment.
I'm sorry, I'm
No problem.
repeating the same stuff, but
That's okay.
so
Yeah.
there's like
Okay.
I'll give you an extra minute, 3 minutes, because this is
Hang on. Let me just. Yeah.
yes. Okay, we are back up on the screen, but it's not full screen.
But it's yes. Hang on. Yeah. Okay. Is that?
That is fine.
This is
Continue.
actually,
Continue.
yeah. And I mean, till when was I audible? Did I till the point when I defined the metric, was it audible or was it not so?
Yes, I think so. Yeah, that was done, but I guess you were you went.
Yeah, I was
past
just
the
saying what this hyperbolic
Mobius
three-dimensional metric.
transformation or something, and then yeah. Okay.
Yeah. So these Mobius transformations are these finitely many symmetries where Z goes to AZ plus B by CZ plus D. So those guys are actually now symmetries of this extra one dimension. I mean, see, I'll say what this is about. See, it's the best way to think of it is that, look, if you are really trying to study the geometry of say a usual three-dimensional tree that you sit around, that you see around you, then the foliage is something that's on the surface of the tree. It's a two-dimensional gadget. So somehow the geometry of in 3 dimensions has a kind of a trace that it leaves on its boundary, which is some kind of a fractal. Yeah. So it's 3-dimensional geometry versus 2-dimensional conformal structure. That's the point of this. Yeah. So this was known to Poincare. And so these conformal symmetries, Z goes to AZ plus B by CZ plus D, these complex analytic objects, those reflect in terms, I mean, they are the best kind of symmetries of a geometry which preserve distances. So you don't have distances on the Riemann sphere, but you do have distances if you go one dimension up. Yeah. And so what was the question here? So basically, instead of looking at this discrete group of symmetries, discrete group of 2x2 matrix elements, you can look at them as acting on this nice space, which is more or less like Euclidean space, except with the scale factor. And then again, you can pass to the quotient by removing these extra symmetries. That gives you something which is locally three-dimensional, sort of looks like the universe we live in, but it has a certain feature. Yeah, somehow the geometry is trapped in a certain geometrically significant part. This part is what's called the convex score, which means essentially you look at all closed geodesics, closed shortest paths, and all the closed shortest paths are contained in this core. So think of the core not technically, but just as something which is the geometrically significant part of the manifold. Yeah. So that's what's called the convex core. Technically, it contains all closed geodesics, all closed paths which go round and round and round and round, and that's really what is going to capture for us this I mean, it captures the geometry of this manifold. Yeah, it captures the geometry of this group. Yeah. So essentially, you quotient out by this group of symmetries, you have this manifold. That's what you're really looking at from this three-dimensional geometric point of view. There is an exact dictionary between this three-dimensional perspective and the two-dimensional perspective that we have been talking about so far.
Okay. Mahan, maybe maybe in a minute or so you can.
This is my last slide.
Okay, thank you. Sorry. Yeah. Okay.
So the question is basically what happens. I mean, what are so Sabya mentioned this thing about what happens if you look at the entire family of dynamical systems. Well, amongst these dynamical systems, things which would be nice is if you kick the dynamical system a little bit, it does not change qualitative behavior. That's what's called stability, structural stability. Yeah? And so here are two theorems about structural stability, one on the Kleinian group side, one on the complex dynamics side. So Sullivan basically showed that this kind of, on the Kleinian group side, a group is structurally stable. That means the dynamics does not change under small perturbations if and only if this convex score, the geometrically significant part that I talked about in the previous slide, is actually compact. It's some bounded object. He proved a very similar kind of theorem and using similar techniques, transporting between these two. He essentially showed on the side of complex dynamics, look at rational maps which are structurally stable, and those are essentially everything except some stuff that happens on the boundary of the parameter space. So what's the upshot? The upshot is basically that he set up this dictionary to go between these two completely different kinds of dynamical systems, one iteration of polynomial, the other iteration of, say, linear maps, but finitely many of them, and gave us a way of actually using techniques to go between these two worlds. Okay, so thank you very much.
Thank you, Mahan. There's a big round of applause. We should give a bigger round of applause, please, to all the three speakers. Mahan, thank you very much. Thank you for doing it from online. I'm sorry, we missed you here. Definitely, with we could see your animated lecturing style. We missed it here, but thank you for joining from France. Yes, there is a question in the auditorium. Amol Dighe has a question. Amol.
So Mahan, the one impression I got was this Alfor's finiteness theorem is applicable for maps of the kind AZ plus B by CZ plus D, whereas this Sullivan's wandering this theorem is applicable for all rational maps. Is that a correct impression, or are the theorems more general than this?
So here's the thing. I mean, alpha. So for instance, what is so there? Yeah. So Alfor's finiteness theorem is for finitely many maps of the form Z goes to AZ plus B by CZ plus D. Okay. So you take finitely many of these gadgets, throw them in, and look at the dynamics. That's where so it's look at, say, for example, two linear guys, as opposed to one quadratic guy, and so then you have so the one quadratic guy is where Dennis will apply, Sullivan's thing will apply, and two linear guys is where Alfor's will apply. So there is a common generalization possible. Just take finitely many of arbitrary degree. That's a more complicated system.
Okay, and one more question.
It's actually for Sabyasachi. So of course, this wandering theorem you said is applicable for all rational functions, particularly the example of a polynomial. Is it more difficult to prove it for polynomial, or is it more difficult to go from polynomial to rational? Or
no, the proof that Sullivan gave was for rational maps. It was for all rational maps, and the same proof works.
Okay.
Jyotishman,
yes.
There was a question about this biology thing that had come up just after Sabya's talk.
Yeah,
So,
I was
let
there.
me-
Yeah, Professor Dua from, I think, London was trying to.
Yeah. So there is something which is a different but more qualitative answer to your question, which is essentially that, I mean, whenever you have a system that is trying to maximize surface area, if something tries to minimize surface area, you have essentially, say, the shape of a sphere. What happens if something tries to maximize surface area? So, for example, trees are trying to absorb largest amount of sunlight. Say sea anemones they are going to try to maximize surface area to get the largest amount of food possible. What happens is that the geometry, the intrinsic geometry, turns out to be this hyperbolic geometry that I was talking about, and the surface turns out to be this kind of fractal that has shown up in the last two talks. So whenever you see some kind of fractal behavior, hunt for hyperbolic geometry in one higher dimension. Almost surely there is going to be some such thing. The human brain tries to multiply, and the lungs, etc., etc. So that's trying to maximize surface area, and then that geometry versus this fractal dynamics. It comes up all the time.
Okay.
But can I add? But then there is a limit. So far as the evolution has put a limit, if the size of the brain keeps on increasing, there won't be, that fetus will abort. So that limit has to be set by certain parameters which are intrinsic at the physical level by mathematics and physics.
That's correct. So there is a theorem of David Hilbert from around 1900. So nature, of course, knew this long before, which basically says that none of these negatively curved objects can be completely embedded in our three-dimensional Euclidean space. So there is a natural boundary that the mathematics dictates.
Yes.
Okay. Nice. Okay.
Thank
you, Mahan. Thank you. Any other questions to all the three speakers? Anish, Sabyasachi, and Mahan, they gave wonderful talks, but please, are there any questions from the Zoom audience?
But I'm looking only for the application of this as summarized by three speakers to a person who doesn't come from the field of mathematics.
Right. So I don't know whom you want to target the question to, but maybe Anish, you can add on something if you want about the application.
Yeah, so I have to admit that it's always a question I dread. But you have to answer for yourself. So the honest answer is that the part that I spoke about does not in fact happen. And I'll add the usual caveat that
I'm sorry, you were the speaker who said that Alfred Nobel did not want prize to go to mathematics for some reason. But he said in his will that this prize should go to the person whose work is important to human welfare. How this work is open for public welfare work, and
that's absolutely that's a very good point. But that's why Sullivan does not get the Nobel Prize, right? So that's why we have got a separate prize in which we take the decision of keeping human welfare to the side for the time being and indulge ourselves a little in art and recognize beauty for its own sake.
Sure. That ultimately it will merge into physics, and that will be applied to that physics. Most of the physicists, they got the Nobel Prize because of their strength from mathematics.
Yeah, I tend to agree with it. The only thing is in ergodic theory, the time scales tend to be kind of long. So maybe at some point in the very long, distant future, somebody will apply this. Thank you.
Thank you, Anish. Thank you.
Professor Mahan's interpretation in biological sciences, I'm going to talk tomorrow in Cambridge University, partly also.
Okay. Thank you, Professor. Thank you very much. Any other parting comments, questions from the audience here or the Zoom? I don't see. any questions? So I would like to conclude this NSF Wednesday colloquium today. It was wonderful to have three mathematicians explain to most of us. Yes,
Hello?
yes.
Yeah.
Was there a question?
So, yeah, no, I mean, no, there's not a
Mahan.
question. It's basically, yeah. So, Sabya mentioned this thing about Dennis being a very colorful person. And I think it's not going to be fair to close without saying something about how colorful Dennis is. So, Dennis was once in Brazil and he got shot. Yeah. So, they tried to mug him and he got shot. So, he drove bleeding with a bullet inside him to a hospital. Yeah, got the bullet removed, and now he wears that bullet like a chain. So
Great.
That's great.
Highly witty. Very, very nice. Excellent.
Okay. Thank you, Mahan, for that anecdote. Thank you very much. Yeah, so we'll close the session today. I thank the auditorium staff for getting the AV set up and ensuring that everything moved smoothly today. I would also like to sort of tell Mahan again that we are missing you here, Mahan, and you're missing some samosas that I have arranged just after this after this session. So you're most welcome. All of you are most welcome to have some tea, coffee, and samosas. So thank you very much. And let's thank the speakers once again, please.
Thank you very much.
Thank you, Zoom audience. Thank you for joining in.
Thank you.